And now that we've developed these ideas, right, now that we've gone through this work of understanding complex numbers, which dropped out of quadratic equations, now we can return, right? Now we can freely, um, make up some quadratics, right? Let's say, x squared plus 4x plus 5 equals 0, and we can use this nice quadratic formula that we derived to solve them, right? We have a equals 1, b equals 4, and c equals 5. As we attempt to solve this, right, we're going to have that x is plus or minus what we called b, which is 4. Sorry, it's negative 4 plus or minus the square root of b squared, which is 16, minus 4 times 1 times 5, all over 2, which is minus 4 plus or minus, looks like we have 16 minus 20, so minus 4 in there, all over 2. And the square root of negative 4 is going to leave us with 2i. That's all over 2. And we get minus 2 plus or minus I. Right? These are our two answers. Right? Go ahead and check these. Right? Do a little bit of practice with this complex multiplication and addition, and plug these two answers into your equation just to make sure that they work. We can do one more that I know will give us complex solutions. So let's say x squared plus 2x plus 2 equals 0. Once again, as we look at this, we're going to see that a is 1, b is 2, and c is 2. But no fear, we have this general formula. We have x is negative 2 plus or minus the square root of 4 minus 4 times 2, which is 8. And that's all over 2. Well, 4 minus 8 is once again going to be minus 4, so it looks like we have minus 2 plus or minus the square root of minus 4 over 2, which is going to be minus 1 plus or minus I. I was like, okay, we do know how to deal with these, but they're not quite as nice, right? Complex numbers are a little bit more involved, a little bit more difficult to work with than our standard real numbers. So the question is, what made this happen, right? Can we find something that tells us whether our solutions are real or complex, right? Is there a way to, at a glance or with a quick calculation, figure it out? And let's take a look at what actually made our numbers complex. Since we arrived at I by trying to take the square root of negative 1, that would tell me that if we're going to run into a problem, it's going to be in this square root. More than that, it's going to be the thing in the square root, right? So what is it about that part of the formula that can get us to run into trouble, right? Let's just write down our formula so we can take a look. We have that x is negative b plus or minus b squared minus 4ac. That's all divided by 2a. So this is our potential problem right here, right? If this is negative, well, then we're going to get two complex solutions, right? Two coming from the fact that we have plus or minus here. And if this is less than 0, then it doesn't matter what the values are, they're always going to be complex, right? So let's write down what we've just discovered. If b squared minus 4ac is negative or less than 0, then we have two complex solutions. Okay, so what about if it's positive? Well, if it's positive, then we can always take the square root of it and get a real number. The real number might be ugly, and we might not be able to write it as a fraction, but it will still be a real number that we can work with. Writing that down, if b squared minus 4ac is greater than 0, right, if it's positive, then we have two real solutions, right? Where in this case, we're not like saying versus made up solutions, right? Real solutions is solutions in the real numbers. And we've covered possibly every value for this, except when that equals 0, right? What happens if b squared minus 4ac equals 0? Well, let's sort of play this out, right? What happens when we have x is negative b over 2a plus or minus the square root of 0? Well, plus or minus the square root of 0 is 0, right? So we just have negative b over 2a. And if x equals negative b over 2a, it doesn't matter what it's plus or minus, right? Because we're adding and subtracting 0. So if this expression equals 0, then we have one real solution. In fact, that solution is negative b over 2a. And what we've discovered here, right, what we've sort of realized, is that this expression here, this b squared minus 4ac, in some ways determines the nature of our quadratic equation. It determines if it's solvable with just the real numbers or not. In fact, it's so important that it actually has a name, right? B squared minus 4ac is called the discriminant, right? Because it tells us what sorts of tools we need in order to solve our quadratic. We have sort of one more quick thing to talk about before this lecture is over. But before we do that, I kind of want to introduce you to a little puzzle. One of the things about math is most of the things that sort of come about in math pretty much all come from just little puzzles. So I'm going to introduce one to you guys, and then I'm going to sort of go over how the last sort of, little bit of our lecture has equipped us with the tools to solve it pretty quickly. So here's our puzzle. It says find two numbers that multiply to 342 and whose difference is 1, right? And could we go through all of the, factors of 342 and look for the two that are in the middle that differ by 1? Sure. But what I want you to notice here is we have two constraints, right? We've been given two constraints. Let's call our numbers, say x and y, and they're subject to the following constraints, right? One, their difference is 1, right? So we might say, y minus x equals 1. And the other one is that x times y is 342. And I claim, and I'll show you, that that's all the information we need. Turns out we have two equations, two variables. We can solve this, right? And I guess I will add for this as well, we need two positive numbers. because that will come into play later. But we can use what's traditionally called the sort of substitution method for this, right? Let's note that we can rewrite this as y equals 1 plus x, and then we can substitute that in here. So we get x times x plus 1 is equal to 342, which means that x squared plus x minus 342 equals 0. And now we can go through the process of doing our quadratic formula, right? So b is 1 plus or minus the square root of 1 squared is 1 minus 4 times 1 times negative 342, and that's all divided by 2. So we have 1 plus or minus 1 plus this times 4 times 342 is 1,368 all over 2. When we add 1 to this, we have 1 plus or minus the square root of 1369 over 2. And then from here, we can recognize, or type it into a calculator, that this here, this is the square root of, or this is the square of 37. So x is 1 plus or minus 37 over 2. So this breaks up into two cases, but I did just realize that we need a negative 1, right? Because we have negative b plus or minus, right? But this will break up into two cases, right? One where we're doing negative 1 plus 37, which gives me 36 over 2. And then when we have negative 1 minus 37, or negative 38 over 2. 36 over 2 is 18, and the second case is 19, or negative 19. And this is where our restriction here becomes important, right? We have two positive numbers that multiply. Well, we got two solutions out. We got a positive number and a negative number. So this must be a false solution. And we have x equals 18. And it turns out, thankfully, that means that y, which is one more than this, is equal to 19. So this seemingly arbitrary puzzle about two random numbers that multiply to 342 and have a difference of 1, that can be solved with a simple quadratic. All right, now that we've done that little puzzle, we're going to take a quick look at some higher order polynomials. And for the most part, our study of higher order polynomials will be done much later in the quarter. But one of the really nice things that we can actually do is we can use some of our quadratic tools to solve them if we're a little bit clever about it. Say you want to solve something like this, right? X to the 4th minus 13x squared plus 40 equals 0. And right away, it would seem to be that we're stuck, right? We haven't developed tools for this, not at all. But let me show you a fun little shift in perspective that will allow us to solve this with relative ease. One of the things about our exponent rules is I can write x to the 4th like this: x squared squared minus 13x squared plus 40 equals 0. Then we're going to do a little bit something that we generally call u substitution, right? And that's picking a clever value for some variable u that will transform this into a quadratic, right? So let's set u equal to x squared. And when we do that, we get u squared, because we have x squared squared, minus 13u plus 40 equals 0. And this is a quadratic in u. We can factor this just like we'd factor any quadratic, right? We can factor this into, we need two numbers that multiply to 40 and add to negative 13. I'm going to call that negative 8 and negative 5. And by the zero product property, we have that u equals 5 or u equals 8. But here, we know that u equals x squared, so we can go back into talking about x's, right? And we have x squared equals 5 or x squared equals 8, right? And now that we've done this, right, we can take square roots, right? We can have that x is plus or minus 5 and x is plus or minus the square root of 8. Sorry, that's a square root of 5. I wrote the right thing and said the wrong thing. But by doing this, right, just by shifting what we're talking about, we took a question that we before now like would not have been able to solve without a calculator, and with some clever manipulation got our 4 solutions, right? What about something like this, right? Let's try x to the 1/3 plus x to the 1/6 minus 2 equals 0, right? We want to find a way to shift our perspective to turn this into a quadratic. And I'll offer you this one, right? What if u is equal to the x to the 1/6, right? What happens when I square that? Well, x to the 1/6 squared is x to the 2/6 or x to the 1/3, right? So u squared is x to the 1/6 squared, which is x to the 1/3. So this now becomes u plus, or u squared plus u minus 2 equals 0. Okay, so now we can factor this, right? We can factor this into, say, u minus 2 or u plus 2 and u minus 1. Well, that would tell me two answers, right? That would say that u is equal to 1 and negative 2, but u is equal to the x to the 1/6, right? So that means that x to the 1/6 equals 1 and x to the 1/6 equals 2, equals negative 2. And so I need to raise both of these to the 6th power, right? And 1 to the 6th power is 1, and negative 2 to the 6th power is 64. So now we have two answers. We have x equals 1 and x equals 64. But one of the things that we need to be careful about here, right? We need to be careful with our answers here when we have fractional exponents. When we have fractional exponents, we might end up adding extra solutions through this process. And the way we can fix that is simply by checking our answers, right? So let's check. Let's check x equals 1. 1 to the 1/3 plus 1 to the 1/6 minus 2 is 1 plus 1 minus 2, which does equal 0. So we're good. But what about x equals 64? 64 to the 1/3 plus 64 to the 1/6 minus 2. Rather than right away trying to calculate the cube root of 64 if you don't know it off the top of your head, is recognize that 64 to the 1/6 is 2, and so it would be the square root of whatever this is, right? Because we need to multiply 1/3 by 1/2 to get 1/6. So that means that this should be 4. And this is all in green. So 4 plus 2 minus 2 equals 4, which does not equal 0. So, turned out x equals 64 is a false solution, and our solution to this equation, by transforming it into a quadratic, is x equals 1. And I know that this may seem a little bit strange, right? Uh, Somewhat odd and complicated, because u is different in each one of these times. So I'm going to do a couple more to sort of finish out the lecture, um, just to sort of show you sort of what the process looks like trying to solve these, right? So let's try this one, right? Let's try x to the 6th minus 2x cubed minus 3 equals 0. I want to transform this into a quadratic. So I'm looking for a value of u such that one of these looks like the square of the other. Well, it would look to me like I should set u equal to x cubed, because that would mean that u squared is x to the 6th. So that means that our equation here is actually u squared minus 2u minus 3 equals 0. And that's easily factorable, right? That factors down into x minus 3 and x plus 1. Or sorry, u. These are both u's because we're currently in the u world. And that will give me my two solutions, right? That'll give me u equals 3 and negative 1. And now I need to look at my values in terms of x, right? So x cubed, go to my eraser, this should be blue. X cubed equals 3, and x cubed is negative 1. So if we take cube roots, we're good, right? If we say x equals the cube root of 3, and x equals the cube root of negative 1 is just negative 1, those are our two solutions. I'll do one more with fractional exponents for you. Let's try this one. So the square root of x minus 3 times the fourth root of x minus 4 equals 0. Once again, we're wanting to find values such that I can make one of these look like the square of the other. Let's translate this first, though, into fractional exponents, and maybe it'll be more obvious. The square root of x is x to the 1/2, minus 3 times x to the 1/4, minus 4 equals 0. From here, let's try setting u equal to x to the 1/4, which means that u squared is x to the 1/2. Okay? Now we can take this into the u world, right? Because x to the 1/2 is u squared minus 3 times u minus 4. This factors pretty quickly into u minus 4 and u plus 1. And so we can read off that u is equal to 4 and negative 1. Okay, so now we can go back into the x domain, and we can say that x to the 1/4 equals 4, x to the 1/4 equals negative 1. So now we need to raise each of these sides to the 4th power. 4 to the 4th is 256, and negative 1 to the 4th is positive 1. But now we need to check our answers, right? Whenever you're dealing with fractional exponents, and honestly, as often as you can, you do want to check the solutions that we get out of these processes. Okay, so let's check x equals 256. Well, when we check x equals 256, we need the square root of 256 minus 3 times the fourth root, of 256 minus 4. The square root of 256 is going to be 16, right? Because it's the square of the fourth root, which we know to be 4. So we have 16 minus 3 times 4 minus 4. And this is 16, and this is negative 16. So we have that this equals 0, and we're good. Now we can check our final solution of x equals 1. And it looks like we have the square root of 1, which I will just write as 1, minus 3 times 1, or 3, minus 4. That to me looks like negative 6, which does not equal 0. So this solution fails, and we're left with our final solution, just one of them, of x equals 256.